So like I said, the second important measure of correlation is beta. Okay, so this is our second important measure of correlation. And beta, like our correlation coefficient rho, measures how much two random variables tend to move together, but now it's got more information for us. It's going to include differences in amplitude of returns. And beta is computed not really from a hairy formula like this one. Beta is most commonly computed directly from a linear regression. And we are going to need to know how linear regressions work, so let's spend a little time on it. So how does linear regression work and how does it give us beta? So let's say we have a set of returns for some stock asset X. Let's say that's the SPY ETF, and Y, which could be another ETF. So what we want to do is plot those returns exactly the way that we plotted them over here, and then try and draw the best line we can through those returns. And that's what a linear regression does. And when you do that, we're finding this line, the return, which says in English, the returns of y are equal to alpha plus beta times the return of x plus some amount of error. And linear regression finds this line such that the error is minimized, and it uses a least squares method to do that, which we don't have to worry about. But beta, when we do this line, when we make this line, beta is going to be the slope of the line. So I did a real regression for us here. Again, I've got just our 4 periods of data to keep it simple. So when the return of x was equal to minus 0.55%, the return of y was minus almost 1%, and etc. for the other 3 cases. And then I used Excel's regression function to create this regression and to plot it for us. So I've got returns of x here on the x-axis, and on the y-axis here I have my returns of y. So the blue diamonds are what I pulled directly from the real world data, okay? And then the regression gave me the line that goes through the orange squares. That's the line that best fits the data that I have. And so what it gave me was alpha was very small, negative number, and that's the intercept of the line. That's this little bit of line right here. It answers the question, when the returns of x are 0, whoops, what do we think the returns of y will be? And it's saying to us, when the return of x is 0, the return of y will be very, very small, negative. Okay, and then beta is the slope of this line. And as you can see, it looks pretty good here, about 1.61. So let me just get my slope of this line here. Here's our beta, and down here is our alpha. And then we also get out of this something that is extremely helpful and important. That's the r squared of the regression, and the r squared tells us how much of y's behavior is explained by x's behavior. So if we go back to our graph over here where we were looking at rho, here we'd say if we did a regression of this, r squared, if we did a regression, would be similar to 0, which would mean that we really cannot explain the returns of y based on the returns of x. We just can't figure out what's a good line going through this data. So here are some examples of the same things that we saw with the correlation coefficient. So this is return of x here, and this is on the y-axis, return of y, okay? And we've got positive beta, negative beta, and beta equals 0, when you just can't really draw a good line. So this would be our r squared equals, let's say similar to 0, okay? And this probably, I'm going to guess, would have, I'm just guessing here, an r squared similar to something like 65%, and that's probably here too. So R squared is similar to something like 65%, okay? And just to go back over here, this would have an R squared similar to 99, let's say 95%, something like that. So that's how the R squared comes into this. Okay, I think we've got it. Like I said, typically the beta comes out of a regression analysis. There is, however, another hairy formula for beta, okay? So you don't need to know this one, but you should know, here's another formula for beta that's very simple, and all we need to compute beta of asset B to A is its correlation coefficient and the standard deviation of the returns of B divided by the standard deviation of returns of A. So you should know this one. Okay, because this is a simple formula. If I give you a correlation coefficient and two standard deviations, I will expect you to be able to compute the beta. Okay, so now let's look at how beta and rho compare. Remember we said they were similar but not exactly the same. Rho is a measure of correlation that does not include amplitude effects, and beta is a measure of correlation that does include amplitude effects. So I think I can illustrate this for you very easily by showing you the returns of asset A, B, C, D on this graph. So I've got here on the x-axis, I have the period that I'm looking at, and on the y-axis here, I've got my return for you. And so here's my data. So in period 1, A is down by 0.75%, B is down by twice that, C is exactly opposite A, and D is opposite A, but with twice the amplitude, twice as big as A. Okay, and then I go through this for all 4 periods, and I draw the behavior of A, which is here in period 1. You see it's down by minus 0.75%. They all go through 0, and in period 4, it's up by 0.75%. And you see here that we have for B, B looks just like A, except it's got double the amplitude, right? It's got that steeper slope. So when A is down, B is down more, A is down, B is down more, A is up, B is up more, A is up more, B is up even more, etc. And then we see for asset C is just literally exactly opposite A. When A is down by 0.75%, C is up by 0.75%. So you see that up here, and etc. And then D is just like C, but again with twice the amplitude. And I've also computed for us the expected value for the returns of A, B, C, and D. They all go through 0, so that better be equal to 0, which it does. And I've also computed for us the standard deviations. And you can also see here that the standard deviation of B is twice A. The standard deviation of C is equal to A. That's because all the terms in standard deviation are squared. So even though there are negatives here, everything gets squared. So if the amplitudes are the same, the standard deviations are the same. And D has the same standard deviation as B, which is, again, twice A. Okay, so now let's compare our rho and beta statistics for these returns. That's what I really want to get us to here. Okay, so what do we have here? If we look at rhos, remember rho does not include amplitude effects. So the correlation coefficient of A and B, even though B's amplitude is twice A, it's moving in the exact same direction, so it gives us a correlation coefficient of 1. And if we look at the beta of B compared to A, of course the beta and the rho of A to A are going to be 1, but if we look at the beta of B to A, it's not 1, it's 2 because of the amplitude effect. Okay, so 2.0 beta versus 1.0 rho comes from amplitude measuring in beta, but not rho. And if we follow this through, we see the same thing with C has the same amplitude, remember, as A, but it's just opposite. So we get a -1 beta. And D is opposite A, but with double the amplitude. So we get a -2. So you see the difference here. Rho and beta are directionally the same, but rho is constrained to be within +1 and +1, and no such restriction for beta. So beta gives us more information. So now that we know about beta and rho, what they do, how they work, let's see how to use them. So these are used by investors, asset managers. Oh, they're used all over the place in finance for two main reasons. One is to help build those diversified portfolios. We're going to focus on stocks, but it could be stocks, bonds, or whatever. Remember that diversified portfolio reduces our risk so much. I can't stand it. I can't show you this graph too much. Take advantage of this benefit of diversification. So correlation coefficients are what help us get there, and betas. So how are we going to do this? As usual, you got to know what's our mission in life, what's our investment mission, and then we're going to build a portfolio of mission-fitting investments that now have big differences in beta or rho. And we can use either one. And that's going to give us, if we do that, if we build our portfolio that way, everything fits our mission, but we try to find the set of possibilities for that mission that have big differences in beta and rho, that'll give us a nicely diversified portfolio. So as always with our model-based strategies in finance, something is wrong. It's just true every time. I'm sorry, but that's just life in the Big Apple. Okay, so first thing is, are correlations static? And the answer, unfortunately, is no. Correlations all tend to 1.0 in macro econ declines, i.e. recessions induced by something like we're seeing today in March of 2020, the coronavirus outbreak, recessions that we saw in 2008-9 in what has been called, at least until 2020, the Great Recession, the greatest recession up to that point before not including the Great Depression. Does the future look like the past? Often no. We've looked at some graphs of that, showing that, for example, companies that get into the S&P 500 get out of there very quickly because they start doing badly. And for any company, as it grows, it changes its markets. If we look at Apple of 30 years ago, it's a completely different company than Apple of today. And finally, what's another flaw with this approach? What does this model tell entrepreneurs? Well, entrepreneurs generally are encouraged to put all their eggs in one basket. And so really what this is telling entrepreneurs is don't be an entrepreneur. And of course, that's something, especially in America, where we have a lot of entrepreneurs, people don't want to hear. And all of the greatest companies I can think of were started by someone who was extremely passionate about their vision for the company, and they certainly put all their eggs into that basket. That would include Mark Zuckerberg, Bill Gates, Steve Jobs, etc., up and down the line. So as usual, our modeling approach is not perfect. It's got some assumptions built into it, like correlations are static, the future will look like the past, and if we're smart, we're not going to be an entrepreneur, which all three of those assumptions are not necessarily always correct.